elements, mu k, I think. Is
So
minus 1 before the mu in this matrix. I don't know why there is minus 1 before.
I think it's a transformation you need to get into this. I mean, you put this something different. You may okay. So you put something different here. So you may choose this in a different way. Mm-hmm. Then you will get a different condition here. Okay? Then, so this equation that I'm solving here will look. At the end, you are going to get the same thing. But of course, these equations are, this equation is going to look different because, well, your U and B are defined different. But at the end, the solutions, you should get the same. Okay. You know what I mean? So if you change this definition, you will change, you will get something different here. Mm-hmm. And this condition will be different. Mm-hmm. And then you will just get different U's and B because, well, you define it different. Mm-hmm. But then when you substitute it back in your equation, you should get the same.
Okay.
Okay. So in principle, you can just so the only thing you need is just to have this linear combination. That's the only requirement. You can choose here whatever matrix you want. It's just a linear combination of these two operators. And then you will choose them in such a way that this, that this commutation relation is preserved, right? Okay. This maybe will give you a different equation. You define this B and Q different, you may get something different here. Then all your conditions are going to be different, and your V's are going to be different. But when you put it back, you will get the same because you are changing everything. So at the end, you should get the same. Okay? I had a look at this paper, but I think there is a difference because in the Raju Adressa house there is no spin split. So there is no. If I understood what you have in this paper, if I understood correctly, what you saw there is just the contours of the Fermione. Below the Fermione, there is a break of Kramer's degeneracy. So this Kramer. Okay. So when you have this Raju and Dressel house, okay, so let's say you have Rajva, and in this particular case, you have a cycle here, you have the other cycle here. Sorry. Let's put in this. What is the? Okay. Yes, usually. Okay, so this is the case with Rajva. Let's say Rajva and Rajva, and then you get this cycle here, and then you get this other cycle here. Okay? The two cycles. But in this system, you have this Kramer degeneracy, meaning at the k equals 0, the spectrum is degenerate. So you have all the cross at k equals 0. But at least what I read in this paper is that they don't have this. So in this system that they have, you have these contours, but the spectrum, the Kramer degeneracy is broken. So there is a gap in here somehow. So I don't know how it looks below because they have only this picture with the Fermi contour. So I don't know what happened below in the system, but it could be something like this. I don't know. I would suspect that maybe something like this. Something like this. So that you have a gap. So then you have a gap, the situation changes because so the density of in one of these branches is going to be different to the density in the other branch. Okay.
But the density is density measurement? Because I think.
The density of particles, the density of states, let's say.
Oh, you mean maybe counts? I mean, so one spin will be more than the other spin.
Right, which in this altered magnet is not typical, I guess, because I think the thing of the altered magnet is that there is no net magnetization, so there is no. So I think that is the special thing of so in the magnets, you break this Kramer degeneracy, but when you break it, then you get spin polarization, you get more.
Yeah, exactly.
In other material, like in semiconductors that are non-magnetic, there is no spin polarization, but you have this Kramer degeneracy. So, and then, so there is no net spin polarization. On average, the spin is zero on average. And I think the key thing of this altered magnet is that you still get no net spin polarization, even if you break this Kramer degeneracy. So I don't know exactly how these bands look below.
Okay.
But yeah, the contours are really the same, like for this Rajchandra house. Yeah, I don't know if this is breaking is relevant for something. I don't know because I didn't read the paper. I just read a little bit.
Okay.
But this is clearly mentioned in the paper that this Kramer degeneracy is broken there, which is not the same for the Rajman Andres house.
Okay, thank you.
All right, so let's continue with the lecture. So, all right, so we have the Hamiltonian, the BCS Hamiltonian, have this part which is the condensate energy, and then this part describes excitations, and the energy bands coming from this excitation, at least for a particle that have a parabolic dispersion, looks like we have here. So this branch here is like a whole branch. You see they have negative mass, because the curvature is like the whole bands in semiconductors, and here they have positive curvature. So the velocity here is in one direction, and here is opposite, so it's there are opposite directions. Okay, so this is what you have if there is no superconductivity. What you will have is this. Then you have superconductivity. Then you open this gap here, and this gap will protect your superconductivity. So we have now the energy, so let's have a look at what happened with the density of states. So the density of states is essentially the sum over all occupied state, so or energy state that you have, okay? It's just by definition this quantity here. And so you can make a trick and go from K, from the sum over K to an integral over density of states. So I think I use this in, let me see. I think I have written this for, not sure what happened to this slide, but lost in the wind. Yeah. I'm missing some slides. Let me see. Okay, I think they can't hear. Okay, so we end up with this. All right. The weight shifted somehow. All right, so we have this, and now the question is, well, what is delta? How we get delta, right? And then I will go to the end because the slides are misplaced. Okay, so what is delta? I make a couple of assumptions for this delta, which again is not general, but for the purpose of this lecture, it will be fine. So I will say delta is independent of momentum and is a real quantity, okay? So there is an approximation. This slide also is not here. Okay, when we have this potential, right, this effective potential, we'll go back to this figure, the beginning. We have this effective potential. So one of the approximation that Bardeen, Cooper, and Schrieffer did is to simplify this potential. And they did something very clever that miraculous work, because if you see the approximation that I want to show you now, compared to this, you say, well, this won't work. The approximation is this. So this is the potential, this is the frequency. Here, so instead of WQ, so WQ is the frequency of the phonons, and the maximum frequency they can have is the device frequency. So they put here device frequency instead of they put here minus device frequency. Okay. So I will just look at the energy in here because outside will be repulsive, so I won't have any. And now, so they say, okay, here my potential will be 0. Here will be 0. And here, instead of this, I will put it constant here. At some value minus V naught. And this V naught is some value, okay? Some material specific value, which is related actually to the strength of this electron-phonon interaction in the material. So this is the approximation for the potential. And then, so the effective potential that I have then in my equation for the gap, so here, I think there is a slide still missing. I don't know where it goes, but anyway. So we have an expression for the deltas. Okay, so let me explain what I did for this. Maybe I will do this so that I don't have to. Okay. And then when we're defining this delta value, okay, so we have this expression for delta here. Okay? Now what I can do is, instead of using C, I can put C as a function of the gammas. And the gammas have these U and B's, which I already calculate. And eventually, if you do that, I'm missing the slide here, but I will put it when I, so that available to you. So when you put these U's in there, so that's what you would get to the delta. Here you will have these B effectives that I am putting now like B naught. So essentially the deltas have a minus here, minus 1 over n, so the potential is minus B naught, so the minus just will give you a plus, and then you get B naught here. And then the deltas, which I'm assuming now that is momentum independent, so I just put delta 0, it doesn't depend on momentum. This is essentially, in principle, a cell-consistent equation that you have to resolve, because you have delta on one side, and you have delta also in the sum. Okay. Now, from this expression here, and by the way, these are the Fermi distribution here, NF. So I can divide by delta naught if delta is different from 0, and I will get this equation. And this equation is essentially the equation for the gap. The gap is here, and from this, I can calculate the gap, okay? So I have a sum here over K, and typically you do this trick to go from a sum over K into a sum over energy by introducing the density of states. And you can do this, by using this mathematical relation here. So let's say you have a sum of a function that depend of an energy that depend on K, then you can use this trick of introducing the delta function, okay? So you have this function in an energy variable, and you see if I compute this, what I will get is just F in psi k prime, because this is just the property of the delta function, right? But now I can put the sum inside and get inside this term. 1 over n, the sum over with the deltas, and this is the density of a state, okay? So then you can transform this sum over K into an integral involving the density of states. So the density of a state here depends on the chemical potential and, of course, this variable of integration. So in this case, what I have is this sum, then I will get just this expression here, this integral. The integration goes from minus infinity to infinity, but I know that outside I will get 0, so I just can cut off the limit of the integration to minus omega d to omega d. All right, so then you get this integral. You can work out this Fermi distribution with this sum. You will get this hyperbolic tangent, and at the end, this is what you get, this expression here. There is another approximation here, is to assume that the density of states close to the Fermi energy does not change much in this interval, which makes sense, at least in this metal that they come, because the Fermi energy is very large and this omega d is small, so they typically really change little. So if it is almost constant inside this interval, I can get it out, okay? And say that this is just the density of a state at the Fermi energy. And then I get this integral. So you can solve this numerically, and this is what you get, okay?
We cannot see the cursor.
Oh. Okay, you can solve this equation here numerically, and this is what you will get, the dependence of delta with the temperature. And you can see at 0 temperature you have the maximum, and then as you increase the temperature, it goes to 0, and when you reach the critical temperature, you have a phase transition, superconductivity is gone, okay? So this allows you to get the values of this superconducting gap as a function of temperature. So beta is 1 over kBT. And there is nothing. So there is also this strain of the spin orbit of the electron phonon interaction. That is something that you should know for the material. So you know V naught, you know the Fermi energy of the material, and the temperature, the Debye frequency for the material, you can then estimate what is the value of the superconducting gap. In the zero temperature, yes?
If I remember correctly, when we talk about like Debye frequency, means the phonon is acoustic mode.
Sorry?
The phonon now is talking about the acoustic mode.
Yeah, these are the ones that have lower energy, because the optical phonons are. So, for the zero temperature limit, so in the zero temperature, the time, this tangent just goes to 1 essentially, because beta goes to infinity. And then you get a simpler integral, so you get this expression here. And on the top of that, if you are in the weak coupling limit, meaning that the electron-phonon interaction is weak, then, this sign hyperbolic, you can approximate it like this exponential. So you get then, you can use this expression for estimating the superconducting gap of the material if you know the Debye frequency, the Fermi energy, and the electron-phonon coupling. So if we want to calculate the critical temperature, so the critical temperature I will calculate it, but making the limit that delta goes to 0. Because when the temperature is going close to Tc, delta goes to 0. So if I put delta equals 0 in my equation, then I should be able to get Tc. So making delta 0 in the gap equation, so you will get this relation here. You solve the integrals, and you get finally this expression here. In which there is a constant here. This is a Euler gamma constant just coming from an integral that will give you this number, this constant. And essentially, you can solve here for the temperature. You will get this relation here, from which you can estimate the critical temperature. So you compare this equation here for the critical temperature and the equation for the superconducting gap, you see that the ratio is actually, this ratio is actually a universal constant, this number here, 3.5. This is a property of this BCS superconductivity. How would it is? Well, for some materials that fulfill the conditions that you are assuming here, which are quite a lot, it works pretty well. Like for the case of tin, for example. So you can have for tin, I think this is like this ratio is 3.46, which is close to this 3.5, right? Now for other superconductors like this, high Tc superconductors or unconventional superconductors, or then some things may not work as well, right? Because, well, the assumptions that we did are not valid anymore, and also this, you will have to improve this approximation for the potential, which is quite crude, right? Any question? Okay, so regarding the density of states, we now know how is the superconducting gap, we know the critical temperature. We want to see what will happen to the density of a state, whether I have a state, whether I don't have a state, at which energies. Okay. So the density of a state for the superconductor, don't confuse with the density of a state of the normal state, which was the one that I calculated before. This one is with the superconductor. This energy here are the energies of the excitations in the superconductor. Okay. So you have this again, this sum over k, and you can make the same trick and go from the sum over k into an integral with the density of states, and eventually you can solve all these integrals here and get something very simple here, which is the density of a state. This is the density of states of the material in the normal state, means at T larger than Tc, when you don't have superconductivity, and then it's multiplied by this value here. So if you plot this density of states as a function of energy, this is what you get. 0 here, and then you have a jump, and then it goes up to this value of 2, this ratio. Why is this important? Because actually, when you do experiments with this, you can measure differential conductance, with a tip on the top of a superconductor, and you will see something very similar in the experiment. So you will see 0 conductance here, because, well, there are no states. The density of a state is 0. And then you will start to have a state here that will contribute to the current, okay? So this is what you can see here. There are, both of them are for aluminum surfaces. They are from different papers, so the samples might be a little bit different, and also different temperature. But you can see here clearly this behavior. This is essentially very similar to what is expected from this density of states from the BCF theory. So 0 here, then you go up, and then you get this decay here, right? So, like here. So 0, go up, and then decay. So what is this important? Because if you measure this, you can measure what is the superconducting gap. What will be the superconducting gap in this figure? So if I look at here, how much is the superconducting gap? Sorry? Right, so it will be, some number here is difficult to say, but it's this value here, okay? Because I see this in the density of a state. It's 0, and it jumps exactly at this value of the superconducting gap. So this is what I see here. So this value here will give me the superconducting gap for this aluminum, which is a few milli-electron volts. So here is micro electron volt. So I think this value here, it will be like, it's very small. Well, it is what it is for this. Oh, because the temperature is high, okay. So you made the temperature higher, so you see that this is not, start to get this width here, which is essentially twice the gap. This width becomes smaller. It's just because, well, the gap becomes smaller when you increase the temperature. Eventually, when you increase too much the temperature, there is no gap anymore at 0. All right, so any question? Clear? All right, so I will jump a little bit of this calculation. The idea is I show you this BCS Hamiltonian in the representation with the operators that are the electron annihilation creation operator, also with the Bogoliubov operators. I want now to find another kind of equation that will allow me to also consider the cases in which, well, this delta is not constant anymore, maybe it depends on position, or also momentum, and the energies or the fields may also depend on position and so on. And for doing that, I will be trying to calculate the Hamiltonian in this so-called BDG approximation. B for Bogoliubov, DG for the Jens. Bogoliubov, the Jens approximation, or BDG approximation. And for this, where I want to go is I want to go to another basis in which my my states look like this. I have two components, and the first component is the creation. I create a particle on this, an excitation on the top of my condensate, and this creates a hole in my condensate. So I'm going to have a picture in which excitations are going to be electron and hole excitation. Okay. So what I need is then to put here the ground state of the BCS wave function and substitute there. So, substitute this expression in my equation. I can use these commutation relations from the form. I know the form of these operators in terms of C and C plus, right? So we can calculate this commutation relation. We can substitute this, and it's a simple math, so you just have to sit and look at it. But at the end, what you get is these two couple of equations for the components of my new state. Okay. And if I rewrite this couple of equations in matrix form, they will look like that. Okay. So what I gain with this, I get, well, I have now Hamiltonian, which have a matrix form, depend on K, and this is the Hamiltonian that we describe my excitation. This is the value of the J Hamiltonian. Now it is in momentum space, depend on K. So if I want to get this in real space, I will have to make the Fourier transform to go to real space. And this is what I can do. So I can go from the, K space into the real space, and then I get an equation for the excitations in the superconductor that is in real space. Now, if you look here, I change here these deltas. Before I have my minus deltas and delta. And the reason is that in most books, actually, you will have this convention. So you may call this minus delta, I will call it delta, and then you have just this, okay? It's just a different notation. So you can write then the Hamiltonian in this form. What is H naught? H naught is the Hamiltonian of the particles, of the electron, of the electronic part, single particle Hamiltonian. Let's say you have just a particle with a potential V, so you have the kinetic energy, chemical potential mu, and the potential, whatever you have, electrostatic potential. You have the deltas on the corners, and then you have on the diagonal, on the bottom of the diagonal, you have minus this H naught, okay? This is just coming from here. So I'm putting, again, this energy of the condensate of the zero of the energy scale. So that's why you get this expression here. All right, so what is important, what is the advantage of this equation is, again, this equation allows you to study excitations in inhomogeneous superconductors. And by inhomogeneous, I mean that things that are in this system depends on position. The field depends on position, or delta depends on position. So then I can actually solve this equation and investigate the excitations through it. Now, when I can apply this equation? Well, this equation, everything that I obtained was using mean field theory. So it's good as long as the mean field theory is valid. So mean field theory neglects fluctuations. So if fluctuations becomes important, then this approximation is not valid anymore, okay? So typically you go to higher temperature and you're close to the critical temperature, you start to have larger fluctuations. So close to the TC, most of the time this BDG equation is not valid anymore because fluctuations are large, mean field approximation is not enough. Okay, so if you solve this equation, you solve this equation for a free electron. So let's say Br is 0, and you just have kinetic energy in mu, and this is the dispersion you will get here. Okay, so you have two branches, this branch and this other one, and this electron-like character is, red indicates the states are have more electron-like character, blue indicates they have more hole-like character. Okay, and you see, well, it makes sense because this, the curvature here is like the curvature for electrons, and here you have a curvature for holes. It's inverse the curvature, like for holes. Okay, so in this simplest or relatively simple derivation, it's long, but it's not so complicated. I neglected the effect of a spin. There was no spin at all there. So what happens if I add a spin? Well, I will get something like that. So this is my Hamiltonian. It's not going to be a 2 by 2 Hamiltonian anymore now. So before I have a 2 by 2 Hamiltonian, because I have 2 degrees of freedom, or 2 kind of particles, electron-like and hole-like. But now I have electron-like, hole-like, but I have electron with the spin up, spin down, hole, spin up, spin down, so I will have 4 degrees of freedom. I will have a 4 by 4 matrix. So this is a 4 by 4 matrix. So H naught is the Hamiltonian of the single particle, which is 2 by 2 if you have a spin. Okay. Here is delta multiplied by the 2 by 2 identity matrix sigma naught. And here I have the time reversal. So essentially, the holes, what is the energy of the hole? Is minus the time reversal of the electrons. Okay. So H naught describe electron-like interaction, and the hole-like interactions are described by the corresponding time reversal. So meaning this tau here are the time reversal operators, which for electrons have this form. Okay. So if you want to, let's say you want to build what will be the Hamiltonian, this BDG Hamiltonian, for a 2-dimensional superconducting material in which you have, let's say, rational spin orbit coupling and Zeeman splitting. What you will do first, well, you just will write the electronic Hamiltonian, single particle, which we know from the previous classes that they have this form. Kinetic energy, mu is the chemical potential, B, whatever electrostatic potential you will have. And of course, this is a 2 by 2 because you have a spin, so you have to multiply here by the identity matrix. Then we have this is a spin orbit coupling, rational spin orbit coupling, and this is the Zeeman interaction. Okay? So this is the Hamiltonian of my electron-like excitation. So this is this block here. What is this other block? Well, I just have to act with my time reversal operators on it and get what is written here. So in principle, I know what I should get even without doing the calculation, because you see what time reversal does. It just changes P to minus P, flip a spin, and change K, okay, so I don't have K here. So just P to minus P. And if I change P to minus P, P squared just remains the same. If I change here P to minus P and sigma to minus sigma, because I'm flipping the spin, this is also remains the same. And if I change sigma to minus sigma, this is going to change the sign. So if you see the time reversal is exactly the same, but well, the last one is changing the sign here from minus to plus. Then you can put this in this block. You can put this term in this other block, and on the diagonal you have this delta, and you have your equation, your BDG Hamiltonian, that you will have to solve most of the cases numerically. There are not very much examples, and you can solve this analytically, right? Because it's in principle, it's a Hamiltonian, it's a system of differential equations. Okay? It's a 4 by 4 Hamiltonian that will give you 4 equations, but each equation will have operators, differential operators, this momentum operator. So in principle, it's a system of 4 coupled differential equations. Okay. Only in situations when you have translational invariance and so on, that you can substitute the operators of momentum just by K, because it's a good quantum number, then you may just do things analytically. All right, so some important things about superconductivity. You can create one of the most important devices for applications, which are called the Josephson junctions. So a Josephson junction is just a device that contains a superconducting material linking to another superconducting material through a normal material. And by normal, I mean that it's non-superconductor. It could be an insulator, it could be a cement conductor, it could be a metal, it could be a ferromagnet, whatever, but something in between these two superconductors, okay? So there is a phenomenon here which is called the Josephson effect, and is that you can pass actually a current through this interface of this insulator. So you can pass a current from one lead to the other if you apply a phase. So as we saw, this superconducting condensate is a condensate of these bosons, which are the Cooper pairs, and collectively they can be described by a single wave function. Okay? So this wave function, we have some amplitude and some phase. In the other superconductor, the same. You have some amplitude and some phase. But these are two non-connected superconductors, so these phases may be different. And what happens in this effect is that the current that you pass will depend on the phase difference between these superconductors. Okay, yes?
This flow superconductor, may not be the same, may be different, even though they are the same material.
They may not be the same, yes.
Even they are.
So you may have the same material, okay? So let's say that you have the same material, there is a magnetic field, anything, then the phase is going to be the same. So the phase difference is going to be 0. But if you put this in a loop and you pass a magnetic field, this magnetic field will, you have a magnetic flux and it will create a phase difference. And this will drive a current. So the current, this just some current, depends on this phase difference. It's proportional to the sign of this phase difference. This will happen when you have an insulator here. If you have a metal or a semiconductor, the story may be different, but if you have an insulator, the current goes like the sign of this phase difference. Okay. So, this is just a picture, but in reality, most of the time, this Johnson junction just look like that. So you just have two superconductors, and in the middle, you might put just an oxide. The oxide is an insulator. And so you have this oxide barrier. What you can do with this Johnson junction? Well, one of the things you can build these squid devices, superconducting quantum interference devices. It's not the one that you will eat, but it helps to make measurements. What you can do with that, so by the way, this is the symbol in electronics for the junction, this cross X, okay? So you can make this device, we have two Johnson junctions, and then if a magnetic flux passes there, so you can measure the changes in the voltage across this device. And these changes in the voltage is very sensitive. And the reason is that you can, the area, so the flux depends on the area of this loop. So if you don't have a purely quantum system, you want to do this with with something that is not a semiconductor. You can also induce some current there. But this ring, in order to see this quantum effect, we have to have a very small radius. And you won't see any changes because the flux is going to be very small because the area is going to be very small. But with a superconductor, you can make this ring on the order of microns, the radius, and then the area is large. And it allows you to, with the small fluxes, you still can, with the small fields, you can still have a large flux because the area is large. So you can measure the oscillation of this voltage with the flux or with the magnetic field that is going through this. And it's very sensible to the flux. You can measure magnetic fluxes of the order of 10 to the minus 15 Tesla per meter square, which is about 100 times larger than, than the magnetic fields generated by the human brain. So it just gives you an idea how sensible these devices are. Okay, so what other application you can find for these Johnson junctions? Quantum computing. So in quantum computing, you will use qubits instead of classical bits. So do you know what a qubit is? What is a qubit? It's a quantum bit. How do I build a qubit? So in a bit, I need two states, right? 0 and 1. So in a qubit, I will also need two states, but two quantum states. Okay. So in a bit, I will have just 0 and 1. In a qubit, I will have 0 and 1, but I will have also superposition because I can have quantum superposition between these states. So a qubit is essentially a two-level system. It's just a system or a conventional qubit, actually. There are different kind of qubits. So you have essentially a state 0, a state 1. Typically, this will be the ground state, this, and then you will have other states here. Of course, you may have other states, but you will like this energy here, this energy difference, to be different from energy difference between other states. Why? Why I would like that?
So you can control it.
So that I'm sure what I'm controlling, I'm sure what I'm measuring when I measure the state. Because if I have, let's say, this, and let's say that I shine light to make a transition from 0 to 1, to flip the state of the qubit, well, then I don't know if it is going from 0 to 1 or maybe from 1 to 2 because they have the same energy. I can also have. So I have to isolate these energies, these two levels, from the rest of the spectrum. Okay, and then I will have a qubit. Okay, so the question is how to build these energy states that I can control very well. So this is what you can do with a circuit containing a Josephson junction. So if you look at the LC circuit, okay, just so you have an inductance and you have a capacitor. So the energy, the total energy in the circuit is the energy of the capacitor, which is the charge squared divided by 2 times the capacity, and the energy of the inductance, which is the flux squared over 2L, so L is the inductance. So the frequency of the circuit is 1 over square root of LC, and I can write this actually in terms of phi, in terms of the frequency I can put, and this is the Hamiltonian. So if I make this circuit small and everything gets quantum effect, so this will get quantized. So to what does this Hamiltonian look like? So it looks like a harmonic oscillator, no? So let's say if you say that Q is the momentum and C is the mass, you will have P squared over 2M plus 1/2, then the mass M omega squared, and then phi plays the role of the position. Okay? So these things are quantized in this system. Q is quantized and phi is also quantized. So they are the analog of the harmonic oscillator in which Q plays the role of momentum and phi the role of position. Okay, so essentially that's what I have. Charge is the analog of P, capacity the analog of the mass, and the flux the analog of position. Now, if I quantize this system, well, it's going to behave the same like a quantum oscillator. So I will have quantum harmonic oscillator. I will have discrete levels, okay? And that's what you get, discrete levels in this LC circuit. You may say, okay, I will use these 2 levels now on the bottom for a qubit. Yes, but no, it's not good. Why is not good? Well, because the difference between any pair of these is the same. So it's not good. I have to break this quadratic potential. The quadratic potential will give me this spectrum. All the levels are equidistant. I have to break this. And the way of breaking this is to use the Josephson junction. Why? Because the Josephson junction, the energy of the Josephson junction just go like the cosine of this flux, right? The currents, okay, this is the potential energy of the Josephson junction. So there are some equations here, I will just keep it there, but it's just this, it just go like the cosine of the flux, okay? And now you expand this cosine in series, you get the phi squared term, but then you start to get also higher orders, 4, and so it breaks this quadratic behavior, and then the levels start to separate a little bit. Okay. So we have here, this will give me the potential for the harmonic oscillator, quadratic in phi, but here is square and all the other higher terms, you will get something like that. So this is the cosine potential, and then you get these 2 levels, but now all the other energy difference are different from these two. So you can isolate this. So, yeah, that is essentially the idea for using the Josephson junctions. So you have the Josephson junction here, and you can build in the qubit with these two lower states. So there are actually different kind of qubits. We have, this is, it's an example of how to build a charge qubit, but there are also flux qubits, so name it, there are like dozens of different kind of qubits that you can do with superconductors, and all of them involve Josephson junctions. Okay, so they are essential for these superconducting qubits. I will skip here a little bit of this. Let me see. Okay, so just to mention, there is a problem with the okay. And let me discuss a little bit about Andreev. So I will put these slides. Maybe in the next class, I have some time, I will discuss a little bit more about the qubit, but I'm going away from what I want. So this other part is important for the other thing. So what happens when you have scattering between two elements? One is superconducting and one is not. Okay. So let's say that you have a normal metal and you put it to a superconductor. Well, different things can happen. Okay. If the Fermi level of this normal metal is somewhere here, so above the gap, then nothing happens. You just go like from a metal to a metal, because there are plenty of states for these electrons in the normal metal to go into the superconductor. But if the Fermi energy of the normal metal is inside this gap, okay, the superconducting gap, then the electron cannot go through, because, well, there is no electronic state, there is no single electron state. All the states that I have are just the Cooper pairs, okay? So the only way this electron have to go into the superconductor if it is formed a superconductor, so a Cooper pair inside the superconductor. And so what happens is, okay, so the electron comes in, it forms a Cooper pair, and then a hole is reflected, okay? If you look for the form of the electron, it's like like this electron with this energy and electron with, maybe just, it's another way to interpret this, maybe. So this is the energy of, this is the zero energy. So it's the energy of the condensate. So if I put here an electron, it cannot go because it's a gap. There is no state for this electron to go, okay? So imagine that I have here one electron, and I have here another electron, okay? Because this is full of electron there because it's a metal, okay? So one picture is that I will see these two electrons coming. These have positive energy, these have negative energy. So the total energy is zero, so they just will go to they will form, they will go in and they form a Cooper pair, okay? So this electron that was here will leave a hole here. Okay? So in this picture, if you just look at the electron, no electron, it's just this. It's essentially like these two electrons going in forming the Cooper pair. If you look at the picture with electrons and hole, so it's like electron comes and a hole is reflected. Okay? So this is called Andreev reflection. Yes?
I have a question is that shouldn't the electron and the hole be upside down? Usually you would expect electron below there.
What do you mean? What's that? Say it again?
No, I think.
So they have the difference thing because, well, they have to form a pair, Cooper pair with different. So. Okay, so this electron is coming here with the spin up, this electron with the spin down, so that they can form the Cooper pair here. Okay? So then you leave a hole here with spin down. Okay? You have your hole here with spin down. So this is Andrea reflection. You can use, if you have a superconductor, you can use this to measure the spin polarization of materials. Why? Because this Andrea reflection is going to be suppressed if you have polarization, okay? So let me put it here, a simple example, okay? And this extreme example of a half metal, in which you have only one spin population, okay? In a half metal, you will have something like this. So this is, let's say, spin up. This is the one for spin down. But the Fermi energy is here. So you have only spin up. So this is 100% polarized, okay? Now you have, let's say you put your half metal here, and you put your superconductor here. Okay? Now your electron here, all of them have spin up. It cannot go through because there is no spin down electron to form the pair. So it will have to be reflected, but normal reflection if the energy is high, but at this point, the reflection is suppressed. So then you can measure, this Andrea reflection, and if you get Andrea reflection, if you have very good Andrea reflection, means that you don't have any spin polarization. If your Andrea reflection start to be suppressed and become smaller and smaller, means you have more and more spin polarization. Okay. So there is this, you can then use a superconducting tip to measure spin polarization in materials. Okay. So with this, any question, by the way, so before?
So the entering reflection means you measure the fold coming up. If you measure,
So if you do an experiment, okay, so let's say that you put this and you want to see what happens. So you pass the current and you measure the differential conductance, let's say, of this device. What you will get? Let's figure it out. I have different possibilities because, I can have two processes of reflection. One is just normal specular reflection. So electron goes in, have some probability to go, it's reflected like an electron. So normal reflection. And then you have this Andrea reflection. Now you measure the current. What will be the current when, the contribution to the current when you have Andrea reflection. So let's say you have one electron, so and you have this, you have conductance just by electron in a clean material. You have a quantum of conductance. So each electron will give you a quantum of conductance to this differential conductance. Okay. So let's say this, let's call G0 the quantum of conductance. So if you measure the conductance, what you will get from normal reflection, so let's say this will be G0 here, you should get, 1 G0, okay? If it's just one electron. But the thing is, when you have Andrea reflection, you have two quantum of conductance because what you are what you are injecting is a Cooper pair that have two electrons. So you will have two times. So if the conductance is completely dominated by Andrea reflection, what you will see is like this. Okay? So let's say this is conductance, this is energy or voltage. So the energy is essentially the same, like, where is this? I can put this up to the voltage or down, okay? Let me call here the voltage. And then you have, let's say, 2 here, 1 here, and here is the conductance, units of this quantum of conductance. If it is completely Andreev dominated, so there is no normal, the only reflection you have is Andreev reflection, then you have 2 below the gap. Okay. Above the gap, well, then it's just normal reflection, so you will get 1. Okay. Just will go like this. Okay. If your spin polarization is large, then this starts to go down, 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 down to 0 if you have 100% polarization. So when you measure how much is this going down, you can then extract the spin polarization. There is a caveat, and is that you need these interfaces to be good, because you also have contributions from the normal reflection, right? So you will try to avoid the effect, to minimize this normal reflection so that you get this. Yes, Andrea.
What's the range of the axis or the typical superconductor?
Sorry?
The range of delta, I mean, the value.
The values of delta
Yeah, it's in the millielectron volt.
is in the millielectron volt, yes.
Yeah, and if we replace this normal metal by semiconductor,
Sorry?
if we replace this side normal metal by semiconductor, there is a band gap. And then also super pure form.
You have what? 2 cells, you have a semiconductor. Yeah, yes, you will have absolutely the same picture here.
But that depends on the gap of the superconductor.
It always depends on where this gap is, where the Fermi energies is. It's all depends on that, yes. But if you have, a superconductor, if you are in the conduction band, you will have essentially this, For the valence band, this doesn't really, its valence band will be like 2 or 3 electron volt below. Except if you have holes. I mean, if it's a superconductor that is p-doped and then you have holes, then you will have the same, but this will be electrons in the conduction band and not on the valence. The valence band and not in the conduction band. Yeah, but this, compared to semiconductor, this gap is extremely small. So, semiconductor typically is around 1 eV or more, but here is just milli-electron volt. Okay. So, any further question? No?
I think this question really is about for the semiconductor, you have a gap.
Yes.
Your Fermi level is at the usually into the gap.
Well, nothing happened then, so you don't have anything.
Then you won't have this.
You don't have nothing. So if you just have an answer. If in an intrinsic semiconductor, when the gap is in the Fermi energy is in the middle of the gap, it's just like an insulator. There are no current. All right. So, any further question? And then see you in a couple of weeks.
Okay.
All right.
Okay, I post a video on the Moodle. You can check. No, I upload it to the YouTube video, but I posted it. So if you want to see, you can go to see the video. Check the Moodle. Okay, thank you.